Why time slows down the faster you go. Cosmic lens. Episode 3. For centuries, scientists believed time was a fixed background ticking away at the same rate everywhere. Isaac Newton described it as absolute, flowing equably without relation to anything external. In Newton's universe, 1 second in London was exactly the same as 1 second on Jupiter, on a speeding train, or inside a rocket. It's a comforting idea. It matches everyday experience. And it's completely wrong. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that demolished this assumption. He called it the special theory of relativity. And at its heart was one radical claim. The speed of light is always the same, no matter how fast you're moving. Here's the cleanest way to see it. Picture a light clock. It's a simple device, two mirrors facing each other, with a particle of light, a photon, bouncing between them. Each bounce is one tick. Now put two identical light clocks side by side, both ticking in perfect sync. They're sitting still relative to each other. Tick, tick, tick. Now take one clock and send it zooming past you at enormous speed. From your perspective, standing still, the moving clock's photon now has to travel a longer path. Instead of bouncing straight up and down, it traces a diagonal zigzag because the whole clock is moving sideways while the photon bounces. Here's the key. Light always moves at the same speed. So if the photon has to cover a longer distance, it takes more time to complete each bounce. From your point of view, the moving clock ticks slower than your stationary one. This is time dilation. Not an illusion, not a trick of perception. Time itself is passing more slowly for the moving clock. This isn't just elegant theory. We've measured time dilation directly, over and over. In 1971, scientists Joseph Haffel and Richard Keating put atomic clocks on commercial airliners and flew them around the world. When they compared them to identical clocks left on the ground, the flying clocks were behind by exactly the amount Einstein predicted. The clocks that traveled fast aged less. Cosmic rays slam into our atmosphere and create particles called muons. Muons decay in about 2.2 microseconds. That's so fast they shouldn't survive the trip from the upper atmosphere to the ground. But because they're moving at 99% of light speed, their internal clocks slow down, and they reach the surface in huge numbers. Time dilation keeps them alive long enough to be detected down here. Every day, the Global Positioning System, GPS, depends on this effect. The satellites orbit at 14,000 kilometers per hour, fast enough that their onboard clocks slow by about 7 microseconds per day compared to ground clocks. If engineers didn't correct for time dilation, GPS would drift by about 10 kilometers every single day. Your map app works because Einstein was right. So why does any of this matter beyond blowing your mind? Because time dilation tells us something profound about reality. Time is not a stage on which events happen. Time is part of the fabric of the universe, and it stretches and warps depending on how you move through space. The faster you move through space, the slower you move through time. They're linked, traded off against each other. This insight reshaped physics, led to nuclear energy, GPS, particle accelerators, and our entire modern understanding of the cosmos. It's the foundation Einstein used to build his general theory of relativity, which added gravity into the picture and showed that mass also bends time. You are, right now, moving through time at a rate that depends on your speed and your distance from massive objects. You're living relativity every second without noticing. The universe doesn't run on a single clock. It runs on billions, each ticking at its own rate, each telling its own version of how long a second lasts. And that is why time slows down the faster you go. Thanks for watching Cosmic Lens. Subscribe for more journeys to the edge of everything.